Welcome viewers. In this video we are going to continue design of a substation equipment foundation in Eurocode. This is a stage 2. In this stage 2 we are going to discuss about the foundation and soil parameters, loads and load combinations. Of course this picture may be giving you a brief introduction about the three type of shallow foundations which we have discussed already during the design philosophy of the equipment foundation in Eurocode. So that was that first one. In the left hand side picture you can see that a single isolated footing. Second one is a combined two pedestal foundations. The third one is a combined three pedestal foundations. So these pictures you can just for illustration, but we are going to look this series of 7 series of video. We are going to look about only the single pedestal isolated footing, and after this we will be in the next video we can able to discuss about the combined two pole and three pole foundation, how that can be differentiate from this single isolated foundation, so that there may be some small changes we need to do for combined foundations apart from these single isolated foundations to fulfill this base slab conditions to resist the bearing pressure and the one-way shear check and punching shear. There will be some slight changes in that combined foundations compared to the isolated foundation that we can discuss after this 7 series of videos. These are the various design stages we need for the design of substation equipment foundation in Eurocode. First one is an overview of calculation, which we have already seen in the first stage of video. The second one is foundation and soil parameter loads and load combinations, which we are going to discuss in this second stage. Third one is a stability check. Fourth one is foundation bolt design. Fifth one is a design of bottom slab. Sixth is a punching and one-way shear for bottom slab. Finally, the design of pedestal. So with this, let me move on to our Excel calculation. In the screen you can see that Excel calculations. So here that in the picture plan view you can see that capital L and capital B are the bottom slab size, and small l and small b are the pedestal size in plan. And coming to the elevation, you can see that small t is the thickness of the bottom slab, capital D is the foundation depth, that is from the ground level to the bottom of the foundation, and small d is the height of the pedestal above ground level to the plinth level. So based upon this picture, we have assumed this foundation sizes as the pedestal is one number for single isolated footing, and the sizes we have assumed as 0.7 by 0.7 meter. Bottom pad slab we can assume as 1.6 by 1.6. So this text should be match the picture. And the depth of foundation capital D 1.5, bottom pad thickness T equal to 0.3 meter, plinth level is 0.3 meter we have assumed. Grade of concrete and grade of steel, which we already considered in during our introduction part materials, so that we can consider here. And density of concrete we all know it is a 25 kilonewton per meter cube, and plan area of bottom slab is just multiplying this L into B. Dry density of soil we have considered as 18 kilonewton per meter cube. These are the assumptions, and foundation depth already we have considered 1.5 meter, and internal friction angle is 25 degree. So the coefficient of sliding between soil and concrete we have considered 2/3 of tan phi, that is tan 24. Angle of internal frictions, it is coming 0.29. We have assumed 24 degree as a angle of internal friction. So net safe bearing capacity at foundation level, which is we can get from the soil report, we are assuming here as 100 kilonewton per meter square. So in this case, sometimes the geotechnical report will not provide the direct soil bearing capacity. Instead of, they will provide the subgrade modulus. So in that case, what we need to do, let me explain. So if they have provided directly the soil bearing capacity, then this line is not applicable. So it is showing not applicable. In case they have provided the only the subgrade modulus in the soil report, don't worry. So I will explain how to derive this subgrade modulus into bearing pressure of the soil. So this subgrade modulus is given in the geotechnical report. So select this, and coming to the soil below the foundations, sometimes it won't be a virgin soil. There may be some filled up soil also. So what we can do is we can assume as a filled up soil with 4 layers. In most of the European countries, they used to lay the foundation over the filled up soil or filled up layers which are more compacted and strength enough more than the virgin soil. So that's why they used to go for developed or compact layers of soil below the foundations. So what I'm going to consider here is a top layer, that is the first layer. We are going to consider EPS 200. Generally this EPS 200 is to be used to resist the frost impact. Most of the Europeans used to have that ice impact on the ground, so this will make frost freezing and thawing, which means the foundation used to float below the foundation level. So that in order to resist that, they used to place various materials below that. So this is one form of material, EPS 200. So according to the thickness and the requirement of the ice freezing effect, they used to they used to decide this thickness. So not only EPS, also XPS, which is a extra effect to provide the freezing this material to be used. So that should be the first layer. So I am here assuming EPS 200, and below that dense sand we can provide, or any kind of material. So dense sand we can assume, and loose sand we are assuming. So there are various drop down list here, we can select from this. And crushed gravel at the fourth layer we are placing. So if you again dense we are providing means, then the net subgrade modulus also get decreased. So we are providing as a crushed gravel. So according to that ESI is nothing but it is a Young's modulus or modulus of elasticity of the material. So this generally we used to get from the local construction manuals. Every nations used to have that. So from that we need to extract this value. This EPS generally it will be provided in the supplier or manufacturer catalog, and these are the thickness we are going to provide below the foundation, 0.2 meter for all the 4 thickness. So by applying these equations we can able to find out the subgrade modulus. Also we need to enter the value, that is 35,000 kilopascal per meter we have entered as assumed value from the geotechnical report. So this value we need to extract from the geotechnical report, that subgrade modulus of virgin soil. So after applying that we are getting this 14,872 kilonewton per meter square as a net subgrade modulus by applying these equations. So once after this subgrade modulus is found, then we need to find out this settlement criteria from the geotechnical report. So geotechnical report used to provide the recommendations, what is a maximum isolated footing, what is a maximum settlement is allowed. So based upon that settlement value we need to enter here. If suppose the geotechnical report is stating that settlement is allowed for 20 mm, we can adapt here 20 mm. But if it is exceeding the 50 mm, we should not go that, because 1997 part 1 en annexure h in notes 4 it is mentioning the settlement should not go beyond 50 mm. So we are assuming here 20 mm now, and the gross SPC is nothing but, in case of subgrade modulus, we need to multiply this net subgrade modulus 14,872 into 20 mm. 20 mm should be converted into meter, that is 20 divided by 1000 we need to apply. So that is what applied here in this equation. So in case if we are going for normal bearing pressure, then this is not applicable. we are having only 127 kilonewton per meter square. 14,872. So by applying this, we are getting 297 kilonewton per meter square. So both the case we can consider whichever is applicable for us. So at present we can consider the soil bearing capacity, so which is 100 kilonewton per meter square, and this net SPC we have assumed is to be added with the density into depth of foundations. In order to make a gross SPC, we are adding this 100 to the 18, the product of density of soil to the foundation depth. So we are getting 127 kilonewton per meter square. So this is a gross SPC at 1.5 meter depth. Now coming to the below ground loads. So here we are going to calculate the overburden soil. So how we are calculating total volume of the excavations we are adding here, that is the length and width of the base slab into the total depth of the foundation from the ground level to the bottom of the foundations, that minus the slab volume we are deducting here and the column volume we are deducting here. So n is a number of pedestal, 1 we have assumed, and small b by small l is the size of the pedestal. D you can see in the picture. So D is a depth below the ground level minus this thickness of the slab. So on looking in this picture and the equations, you can find out the volume of the soil, and this volume of the soil to be multiplied with the density of the soil. So density of the soil, which we already assume is 18 kilonewton per meter cube. So multiplying that, we are getting 44.72. And weight of concrete we can calculate as B into L into T. So BL is a size of the base slab multiplied with the thickness, and plus NBL number of pedestal is 1, small bl is size, and D minus T will provide the clear thickness, clear height of the pedestal below ground level. Adding this above ground level pedestal height, we will be getting the volume. This volume we are multiplying with the density of concrete 25 kilonewton, so 37.58. Adding this to 82.3. So this is excluding the structure weight, not the structure loads are not included here. And this distance we need to calculate. This is a total clear distance of the total foundation, that is top of pedestal and top of ground level up to the plinth level to the bottom of the foundations. So for that we are adding this to small d and capital D. So this is required to find out the maximum bending moment at the base of the soil due to the horizontal force. We will be looking in stability check in the next version. And these two parameters we already discussed in our introduction part. These two are very essential to find out the bearing capacity restrictions. So for limiting eccentricity, if the actual eccentricity due to the moment is more than the limiting eccentricity, there is no issue. That is P by 6 or L by 6. There is no issues. We can do some modification in the bearing pressure calculations accordingly, with in order to find out the point of loss of contact of the foundations. But in no case it should not exceed the maximum eccentricity, that is P by 3 or L by 3. So in that case we need to directly increase the foundation sizes. So these are all about the parameters to be considered while doing the design of foundations. Next we will move on to the foundation loads. These are all the foundation reactions. First, that table 1.1 table is listed for primary loads, which are dead load, live load, conductor tensions, wind loads along X, wind load along Y direction, ice loads, and finally the short circuit forces. So these are the loads we need to consider as a primary, and reference documents should be the document number which is for the structural design, where we can able to find out the foundation forces for this. So these are all the values in highlighted in the green color cells are the input values to be entered here. So for dead load we have considered 9.5, which is a vertical load from the structure due to the self weight of the structures, equipment and the conductor, or any other fixing part. We need to consider this 9.5 kilonewton we have assumed here, and the live load is nothing but it is a 1 kilonewton we have assumed for the workmanship, that person who is going to do the maintenance or installations. We have assumed that he will climb on the structure to install. So for that 100 kg, that is 1 kN, we have considered it is EN 50341, the standard it is mentioned for substation or overhead line transmission tower. Those also we need to arrive from the structure calculations. So accordingly the moment is 6.5 in my directions. So coming to the wind load, here we have assumed as 3 kN. Accordingly the moment my is 8.5. So likewise wind y is 2.5 and 8.5 in mx moment x. Ice load is 0.5 vertical alone, and short circuit force 4 we have considered. Accordingly the moment my is 20. So this is a resultant force. Of course this is a square root of hy squares plus hx squares. So and next to that table 1.2 is a SLS load combinations. So this is simply adding and multiplications of with the factors. So these are the load case which we have discussed during our introduction. So here these are the lists as per the load cases. So this, as per this, we need to arrive these formulations so that all the loads are combined together, applicable loads are combined together in hx and hy, mx, my, vz, that is vertical, and resultant horizontal forces. Next one is a table 1.3 for ULS load cases. So these load combinations are as per class 6.4.3.2 of EN 1990. So accordingly this formulation to be done for hx, hy and mx, my. The same factors like dead load, it is 1.35. So here that dead load cases we have had both live load and dead load here and multiplied with 1.35, and the normal tension it is 1 into conductor tensions we have applied here nt. So 1.5 times the wind. So these are the primary load combinations for ULS cases we have considered here. So this is simply summation and multiplication with the partial factors, no other than that. So with this we can close this second series, and we can look into more detail about the stability in series 3.
Thank you. Look description for more related videos. Subscribe to this channel for more updates. Thank you.